Right. That's actually a very clever idea. Then actually, you can put many lenses and do some signal processing behind, and recombine the data, and get a highly resolved image. Then is the area of synthetic aperture radar. Okay, so what do people do in this field? Well, there's a remote sensing field. So you have a rough terrain. You fly an airplane over the rough terrain. You carry a small antenna. Antenna is rather small because it's say you want to do measurements at 1 gigahertz is what 1 gigahertz 30 centimeters. 100 megahertz would be 3 meters. Okay, so the antenna, in a sense, you want the antenna to be as large as you have, because then you can send in a wave, a microwave, and then look for the echo. Send in the microwave, look for the echo. Send in the microwave, look for the echo. Then this can be thought of as point scatterers from the surface. So with this antenna that the airplane can carry, you will have limited resolution, right? You have a limited resolution because the airplane is only that big. And you want to do measurements at, say, 100 megahertz. Your antenna is so small, it collects so few data points on the thing. So what do you do to make the resolution bigger? Make the resolution better? What do people do in synthetic aperture radar? Do you know? It's a very simple idea, but very clever. Move the plane, right? Move the plane and collect the data point from different angles. Okay, so you have the same scatterer, but then get a different angle of the data from the same scatterer. So you enlarge that angle, and you can synthesize large aperture. The larger the aperture of an antenna, the higher the resolution. Like the larger the aperture of the lens, the higher the resolution. So if you have only very small lens, you can synthesize a large lens by signal processing technique. If you keep out the phase and amplitude of the signal, if you keep track of the phase and amplitude, and recombine them. So that's what people in synthetic aperture radar do. They collect the data that will be in terms of complex data with real and imaginary part. You synthesize them later on by imagining that you have a large aperture. You don't have to make a humongous plane. That would be very expensive. All the taxpayers will have to pay a lot of money to make a humongous plane, right? So we make a small plane, fly it over, hire a lot of clever EM people and signal processing people, process the data, and you get these beautiful images of the Earth's surface. I don't know if you have seen some of this synthetic aperture radar image of the Earth. They are taken at radio frequency and microwaves, and yet they are highly resolved. Okay, highly resolved. That's what people can do. Okay, so somewhat related to this idea of the real identity. Okay. So let's see what are the fun things we can do with this real identity. Well, we don't like double integrals. Many of us do not like double integrals. See if we can convert this integral into a single integral, because then you can spend less computer time to do the computation, and you can also take less time to write it down, right? Otherwise, it's very laborious to write it down. So I'm going to convert this into a integration in cylindrical coordinate system, k rho, dk rho, dphi, right? This will be dkx, dky, d alpha. Let me call it alpha. Okay, so if I have kx, ky, k rho, this is alpha. Then convert my integration into the cylindrical coordinate system, and then it will be 0 to infinity on the cylindrical coordinate system, 0 to 2 pi. And then this will be equal to I over 2 pi with this thing. So let me do a conversion now. This is actually kxx plus kyy, okay, would be just actually k rho dot rho, where k rho is x kx plus y ky, and then rho would just be my x plus y. Okay, so that thing can be written in that manner, and hence this thing can actually be written as e to the I k rho cosine of alpha minus phi. This is just a dot product. This thing is just k rho cosine of alpha minus phi, where I have an x coordinate here, and then the rho vector will make an angle phi. If you take the dot product between that two vectors, you get this quantity over here. Okay, so this can be written as such. This can remain as it is. Okay, let me see where I can put it. I don't have a place to put it. Pardon me for erasing this. So that is equal to that. And now that the alpha integration can be performed in closed form, do you recognize what the alpha integration is now? Bessel function, very good. We just learned the other day that the Bessel function is 1 over 2 pi, 0 to 2 pi, the alpha e to the I k rho dot rho. We just learned the other day, 2 lectures ago maybe, that this is true. And that thing expands to that, and that's just a Bessel function. And hence you can do the integration and end up with this identity that this function is actually I 0 to infinity the k rho over k naught z j0 k rho e to the I k naught z. Okay, that is called it Sommerfeld identity. I think it lives around 1919 too. I don't actually know when, okay, but let's say it's 1920, around that period. I don't exactly recall when he came up with this identity now. But it's a very famous guy. Sommerfeld. Should be an R here, I think. He's a very famous guy because he has 4 or 5 PhD students who won Nobel Prizes, but he himself did not. Okay, so he's a wonderful guy in that sense. Okay, so that is the Sommerfeld identity, which is now in terms of only just one integral, and which is in terms of Bessel functions. And just now you asked me what other functions are complete. Actually, Bessel functions are also complete. You can show that this is true. It has nothing to do with the identity, okay, just about completeness. That this is equal to delta rho minus rho prime over rho prime. This is true. You can prove this identity for about Bessel functions. It takes a bit to prove, but it can be done. Okay, we show that these functions are complete because even the delta function can be expanded in terms of them. Okay. So another thing that we like to do is actually to convert this integration into a infinite integral instead of a semi-infinite integral, because then you can have more fun with it. When you have an infinite integral, then you can do control deformations a lot simpler. So let's try to convert this into an integral of something like this. Okay. And once you have that, then you can do control deformation a lot simpler. And how do we do that? We make use of this Bessel identity that the Bessel function is a standing wave. It's actually equal to half the Henkel wave of the first kind plus the Henkel wave of the second kind. Okay, it's equal to that. And as I said before, this thing is actually 2 over pi k rho cosine of k rho minus pi over 4 when k rho tends to infinity. And you can show that this actually is equal to 2 over I pi k rho e to the I k rho when k rho tends to infinity. These are called the asymptotic expansions of these functions. And then you can show that this is equal to 2 over minus I pi k rho e to the minus I k rho when k rho tends to infinity. And hence, you can actually show that this is actually true. Okay, that you can combine these two, at least from the asymptotic expansions, but it's actually always true, even when k rho is small. This is true for all k rho. Okay. And if you do this, then we can actually break this integral into 2 integrals, one that involves the Henkel function of the first kind, and one that involves the Henkel function of the second kind. So what you have then is that if you go down this route, then this will be equal to I 0 to infinity the k rho, let me not write the k0 anymore. K0z is laborious to write. Let me just write kc, and you know what I mean. Okay. So this is H01. I put a 2 there, okay, but make use of this identity. And then I will have a second part that I can convert, hopefully, into the other half of the integration. And I'm going to make use of this identity that you've never heard of or never seen, but it's given in handbooks. Okay? That the Henkel function of the second kind with this argument is equal to the negative of the Henkel function of the first kind with this argument. Okay? You can find this identity in Abramovich and Stegen, for instance. But why all the fuss about this identity? Why this very peculiar way of writing a minus sign? This is just minus 1, right? Why this peculiar way of writing a minus sign? Does anybody know? The reason is because the Henkel functions behave like log of x when x tends to 0. There is a logarithmic singularity at the origin. So when you take the log of a function, it doesn't matter whether it is e to the I pi. This is a minus 1, and according to the log's rule, is I pi. But if you have a minus sign in this manner, it's minus I pi. So for something with a logarithmic singularity, it doesn't matter what phase you put on the minus sign, because there's a branch cut there. That's what mathematicians say, you have branch cut there. And it doesn't matter whether you go to this minus sign from here to there or from there to there, you get different values. Whether you approach that minus sign from the bottom or you approach the minus sign from the top. Okay, so it does matter whether this is e to the plus I pi or e to the minus I pi. And we're going to use that to convert the second integral. Sorry, the second integral is h2 because I use the second part. Okay, h2. I'm going to convert this h2 into something that looks like h1 and then recombine with the first. Okay, so it takes a little bit of doing. It's almost like magic, but it works. But magic with logic. Okay, there's logic. Magic is logic. So let's see how the logic goes. Okay. So you have that integral over here. I'm going to do a sign change. I'm going to let k rho be minus k rho prime. Okay. So I just do a sign change in hope that I convert this into 0 to minus infinity. So I get 0 to minus infinity. And then I get the k rho prime. The k rho prime wouldn't change because there's a minus sign that goes with this, there's a minus sign that goes with that. And then kz wouldn't change, fine, because kz is actually k naught squared minus kx squared minus ky squared. I forgot to mention that kz actually does become different. It was before, it was this, but kx squared plus ky squared is k rho squared in the cylindrical coordinate system. So kz is now k0 squared minus k rho squared. So you change k rho to minus k rho prime, it doesn't matter. Kz remains the same. Okay? Then I will have h02 minus k rho prime rho. Okay, the argument of this would change, fine. And then I would have e to the I kz z. Kz doesn't change. Okay? I'm going to use the argument that h02 minus k rho prime rho. I'm going to use this identity that if I put a minus k rho here, I should have a h01 with a minus sign. If I take this identity from Abramovich and Staken, okay, and then with a minus e to the I pi k rho prime rho, okay. So if I pick this minus sign in a peculiar way, so that this minus sign is e to the minus I pi k rho prime. If I take this minus sign in a peculiar way, it doesn't matter in all the other parts of the thing. But in this part, it does matter because there's a logarithmic branch point and there's logarithmic branch cut there. So if I replace this minus sign with the e to the minus I pi, then this becomes minus h01 k rho prime rho. Okay, so the I pi and minus I pi cancel each other. And then this can be just replaced with that. And then this thing now has a minus sign that comes from here. I can flip this around and remove that minus sign. Okay, this is it. But k rho prime is just a dummy variable. Okay, I successfully convert the second half into something that goes from minus infinity to 0. So I have a new identity, which I believe is also due to Sommerfeld, that this can also be written as I over 2 minus infinity to infinity. K rho prime is just a dummy variable, so I can call it K rho, doesn't matter. Okay, H01 K rho e to the I K Z. See, K Z is just K naught C, okay? I'm just going to make them the same. And this integral has an advantage in the sense that it goes from minus infinity to infinity. Okay? Are there any questions? You probably get confused by this. You have to go home and meditate about this. Okay, otherwise it's hard to follow this. Okay, almost like magic, right? Suddenly that minus sign disappears and then there's I pi minus I pi and that kind of thing. You know, something to do with branch cuts. And that I have to pick the minus sign in this manner. K rho was originally a positive number. Okay, and then it's now replaced by a negative number times another negative number. Okay, which means that I go in the clockwise direction. So if I look at this negative number, if I have a complex K rho plane, this is the imaginary axis, and this is the real axis. If I contemplate on what this means, that means that a negative number here has to add I pi in the clockwise direction. Okay, this is e to the minus I pi. Is what it means. To relate that to the positive number. So the contour integration has to be such that it goes along here, but goes above the logarithmic branch point at the origin as you integrate. That's the meaning of this. Okay, there's a meaning of this transformation around a logarithmic branch point. If you trace properly as what this logic means. So that is the integration. So this integral is not defined around the origin, because there's a logarithmic branch point there. But if you integrate in this manner, then it's well defined. And you will also pick up the proper branch of the logarithmic branch point in the branch cut. Okay. And again, you have a singularity here, but they're slightly off the ray axis now because you have introduced some loss. Okay, this is when K rho equal to K naught. This is when K rho equals to minus K naught. Right? This is where Kz becomes 0. And K rho equals to K naught and K rho equals to minus K naught. So this thing should be defined as such. And of course you can be clever about it. You can define the contour so that it gets deformed like that. It can deform like that. So that even in the limit of vanishingly small loss and no loss, the integral is still well defined. And Sommerfeld, of course, has his way of defining this. He said, why don't we define this is K rho double prime, K rho prime. Why don't we define the path just to be like this? And so if you have vanishingly small loss, then the two singularities would be there. This would be the singularity due to this one. Okay? And then this is called the Sommerfeld integration path. Because it defines it to be that way so that it's valid when the limit of no loss. Yes? Which one?
The path is required minus
Because this is what this means. Remember we had a positive number, okay, to begin with. Because we started out with K rho being positive. But we want to change this integration into something that involves negative numbers. So one simple way is to just do a simple change of variables. Okay, relate a negative number to a positive number. But in order for this to go through properly, we say that if k rho prime is a negative number of a strange sort, that it has to be something like this, so that I pi and I pi cancel each other. Okay, so that finally when you have this down here, okay, or this I pi and this cancel each other, you have no more phase term over there. Okay, but what does this mean? It means that this negative number, this positive number is related to this negative number by this phase. This phase goes in the clockwise direction. E to the I pi goes in the clockwise direction. Okay? We take this negative number, and because k rho prime now goes from 0 to minus infinity to 0, so it runs over all negative numbers. But actually, it maps to that positive number by this map. So you have to go from here to there with that phase angle addition in a clockwise direction. If you don't understand it, you have to go back and meditate about it, okay?
Why do the E minus I pi means the clockwise direction?
This is complex variables, unless I remember it wrong. Complex variables, e to the I theta, as you increase theta, you go in this direction, right? So if you decrease theta, you go in the opposite direction. This is complex variables, right? This is how a complex number moves as you increase theta. It moves on the complex plane. If z equals to that, and this is the complex z plane. It moves in that manner. Okay, so there's something we haven't dealt with properly, that we have kind of swept things under the rug, which is that this kz function here, kz function is somewhat a controversial function because whenever you take square roots, you have a choice of a plus or minus sign to take. And when you are encountered with that uncertainty, what sign should you take? You say you write a computer program to program this integral or integration of this integral. You evaluate kz or k naught c. It turns out that you have to take the square root sign. And it gives you some trouble, right? Because computer program can come up with a plus or a minus sign. You have to tell the computer what to do, what branch to take of the square root. It gives you a dilemma as to what you should do. Okay, so we have to fix that value. How would we pick kz? Well, of course, the simple thing is that we have to pick kz, the square root, according to physics. It has to correspond to a wave that satisfies radiation condition that it becomes vanishingly small at infinity. So we have to pick it so that if kz becomes a complex number with the real part and the imaginary part, we better pick the square root such that imaginary part of kz is larger than 0. If we pick that branch so the imaginary part of kz is larger than 0, then when z goes to infinity, this thing always becomes vanishingly small. You pick the wrong branch. You pick the wrong branch such that imaginary kz is less than 0. And when z goes to infinity, this thing becomes exponentially large. So this thing. So the correct branch of the square root is that imaginary kz has to be larger than 0. Okay, so when you program this, you have to make sure that that's true. But then if you want to do contour deformation, you need something more sophisticated than that. You need to define branch cuts in order to make this sum of all integrals and sum of all identity properly defined. If you don't define branch cuts, you can end up with very crazy things, right? Like 1 plus 1 is equal to 1 plus square root of minus 1 times square root of minus 1 is equal to 1 plus square root of minus 1 times square root of minus 1, which is 1 plus I times I, which is 1 minus 1 is equal to 0, right? You can go through this proof and get to prove that 1 plus 1 is equal to 0, right? But what's wrong with this proof?
You can give plus or minus.
What is that?
The square root can give plus or minus.
Right, there should be a choice you should make when you take square roots. You have to be very careful to keep track of which choice you make. Otherwise, you can fool people by saying that, oh, 1 plus 1 is equal to 0. Okay? Give me $2. Usually, you give me nothing, right? You can go and trade with people. That's not good. So we have to learn how to pick the proper branch of the square root, especially when we want to detour this contour all over the complex plane. Okay, so let's talk about Riemann sheets and branch cuts then. And that will maybe help you answer your question. How come I find that sometimes the numerator goes to 0 for my Fresnel reflection coefficient, sometimes it's the denominator, because you have to learn how to pick the right branch of the square root when you evaluate those things. You will actually have 4 Riemann sheets to deal with in that problem. Okay, those are the Riemann sheets. Okay, and then if you know how to keep track of Riemann sheets, then it can help you answer some of the paradox that you face. Let's say we have a very simple function, which is just 1 square root sine. And if you were to look at this function, it will have a real part and an imaginary part. Okay? And then on the right-hand side, real part of f is larger than 0. Okay, that is the right-hand side. And then on the left-hand side, you will have imaginary part of f is less than 0. But then, for every value of z, there are 2 possible values of f. So how do we compartmentalize our complex z-plane so that we can actually keep track of everything about the function? How do we divide up our complex z-plane so that we can keep track of what happens to our f? Because every z value maps to 2 values of f. Okay, one way to do that is to use Riemann sheets. Use 2 Riemann sheets. I don't know if I brought the Riemann sheet. I made a Riemann sheet the other day. I don't have the Riemann sheet here, but I'll bring it next time, okay? So you have this thing over here. So what you can do is to imagine that this thing has 2 sheets, the upper Riemann sheet and the lower Riemann sheet. And then you introduce a suture or a branch cut. Okay? It looks like a suture, a surgical suture. I guess in English we call it a suture, right? Which is a surgical thing. You sew things up with things. And then you use the right half plane to map to the top Riemann sheet. So everything on the top Riemann sheet will only map to the right half plane. And then you can imagine that this consists of 2 sheets. Okay? Everything on the bottom Riemann sheet will map to the bottom Riemann sheet. Okay? Everything on the left half plane here will map to the bottom Riemann sheet. Okay? So then the mapping is complete. I miss nothing now. Then the thing is that how do I switch between the top sheet and the bottom sheet? That is not a unique thing.
How do you define the sheet?
I define the sheet that whenever I take the sign so that the real part of this is larger than 0, that function is mapped to the top sheet. And then when I take the square root sign, when then the real part of f is less than 0, I assign it to the bottom Riemann sheet. So there are two sheets there. Okay, I make a Riemann sheet, actually I didn't bring it to class. If you cannot visualize it, I will hand it to you next time, okay? So imagine there are two sheets here, and the way to get from the bottom Riemann sheet and the top Riemann sheet is to this branch cut. You can think of the branch cut is to be like the Great Wall of China. Okay, so when you encounter it, you have two choices. You either jump over the Riemann, the branch cut, or you go below the branch cut. Okay, let's see how the mapping goes. So I think for some of you this is just repetition because you probably have learned about this in a complex variable course. Okay. So if I take Z to be denoted by this complex number where this is positive real number, then square root of Z can be written as square root of C e to the I theta over 2. This is positive real also. I take the branch of the square root here so that this is positive real. Okay, so you can see that as I start with this point over here. Okay, if I start with this point over here, say, which I would call, which will map to, say, this point over here, a point on the top Riemann sheet. Okay, this is my